Okay, this video is going to cover Unit 2, Part 1, Lesson 1 for our calculus class. And in this video, we are going to discuss estimating the derivative. At this point in the class, you should already have a pretty good idea of how to estimate a derivative or what that means, since we've been talking about slopes of secant lines and tangent lines using these definitions already. Here we have the difference quotient, which is essentially a modified form of our slope formula. And we're pointing out in this first definition that the slope of a secant line is essentially the y value of one coordinate and the y value of another coordinate. And the difference between those two coordinates horizontally is this h value in between. On this diagram over here, we can kind of see that. So let's focus on these 2 points first. Here is one coordinate that has both an a and an f of a. In our class, we had been using x and f of x, but the letter is not super important. Then over here, we've got a secondary point. So clearly we've got 2 points, and we can calculate the slope between those 2 points. All we need is both the x and the y coordinate. And again, the x coordinate and the y coordinate from the first term are located here, and the x coordinate, which is the original x coordinate plus some horizontal distance, this horizontal distance, we've got the x coordinate, and we can calculate the y coordinate from it as well. And if our job was to estimate the slope or the steepness at this particular point, well, the slope between these 2 points gives us an estimate. It's not a great estimate, but it is an estimate of slope. Now, if I start sliding this point a little bit closer to point P, if I start picking additional points along the way, then different lines or different slopes can be calculated. This h value continues to get smaller and smaller because as each h value gets smaller and smaller, these data points just tend to be a little bit closer and closer to the original, and the slope of these successive lines gets to be a better and better approximation for the actual slope at this point. And all these purple lines get to be better and better approximations, and we're achieving that by reducing the size of h. We're trying to reduce h towards 0. And that's why our difference quotient, when included with the limit notation, we're saying the difference quotient as h approaches 0, well, that's going to represent our tangent line, or the slope of the tangent line at that point. And that point in this definition is a comma f of a. Last week, as we were talking about this, we were using x and f of x. So again, last week, we were using that definition to find the slope of a point on a curve, and the slope of the, I should say, the tangent line at a point on the curve. And I'd like for us to go through that process one more time here. Now, these were bonus questions on the first test, but this time now you are being asked to do this as a regular occurrence. Not just the slope, but our job is to find the equation of the line that's tangent at this particular point. And let's do so without even looking at a graph. We'll do this just with algebra and calculus. So the definition did state that the slope of the tangent line is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. On the test last week, I saw a lot of students putting an equal sign right here, and it looked like you were trying to say that the limit as h approaches 0 equals something, and that's not quite right. That's incorrect notation. We're saying the limit of this function as h approaches 0 is going to result in some number. So technically speaking, the equal sign should be on the left-hand side. We're saying the slope is equal to the limit of this function as h approaches 0. So I'm using the definition from last week with x's. You, of course, could be using the a notation that was provided at the top of this handout, and that would be just fine too. Since this function is an x cubed, it may be worthwhile to compute what x plus h would look like. I'm sorry, what the function evaluated at x plus h would look like off to the side. So we have x plus h cubed plus 4 times x plus h. And I might just pause the video and complete this off screen. I would recommend that you do the same. Okay, and here's the end result down here. We didn't talk much about this in our pre-calculus class, but you may have seen this elsewhere. But there's a way to expand these binomials, and we can actually skip a couple of these steps, namely these two, and we can actually take the binomial expansion and obtain this part of the result from here to here using what's called Pascal's triangle and binomial expansion. So if you want to look these two phrases up on your own, watch a couple videos on them from other creators, you'll likely be able to pick up on a trick or two and save yourself a little bit of time when doing this type of work. So I didn't leave myself a whole lot of room, so I'm going to cheat a little bit and give myself some space. I'm just going to slide, actually I'll slide all of this over just to give myself plenty of room to work here. And I'm going to copy the result of f of x plus h into the beginning of this difference quotient expression. Okay, so that's the result that we got at the end over here. And so there's f of x plus h. From that, we need to subtract f of x, which is x cubed plus 4x. All of this is to be divided by h. So again, I'm carrying down the equal sign, and I'm retaining the limit notation. And this limit is giving a description on this function. So we're finding the limit of this function as x approaches 0. And that's some number, that's some, or I should say expression, that's some expression. We're saying that the slope is equal to some expression. We're not saying that the limit is equal to something yet. We do have some components that are going to cancel when we subtract. So this x cubed will subtract with this x cubed. This 4x will subtract this 4x. The remaining terms all have an h in common, so all at the same time I'm going to factor out the h. If you're comfortable enough canceling and removing these, that would be okay by me too, but I'm at least going to show this step. And as we finish simplifying here, we can cancel these x's. They factor out, reduce to 1. And lastly, we have the limit as h approaches 0 of the function 3x squared plus 3xh plus h squared plus 4. And now, with direct substitution, we can drop the limit notation. And we now have, as h approaches 0, if these terms become 0 themselves, we're left with 3x squared plus 4. So as a bit of foreshadowing here, let's just pause for a second. This resulting function is what we would call the first derivative function. It's the first derivative function of, in this case, f of x. So this is the first derivative of f of x. And I want you to pay close attention to this function, how it looks, 3x squared plus 4, and then compare that to what we had back here. And as we do more of these this week, I want you to start identifying patterns that you see and see if we can utilize those patterns to essentially skip all of this, because to be perfectly honest, this is a lot of work in this blue section here just to get to our end result. It certainly would be nice to take this original f of x function that we had back here and jump straight to this first derivative. So let's keep that in mind as we move forward this week. Now, the reason why these first derivative functions are so helpful is because this particular function allows us to find the slope at any x value. So if I wanted to find the slope of the tangent line when x is equal to 1, that's easy to do. 3 times 1 squared plus 4. This function gives us the slope at any point on that original curve. And so that looks like 3 plus 4, or 7 to me. whatever that original function looks like, whatever its curves end up creating on a graph, we now know that the slope when x is equal to 1 is equal to 7. That's how steep the line is. We do need a y value to finish out this question, which we don't currently have. So I need to make a note here. The function, when evaluated at 1, was 1 cubed plus 4 times 1. That was our original function. So, well, that's 1 plus 4, that equals 5. So the coordinate that we are talking about, so the coordinate in this original problem that we're talking about is the coordinate 1, comma 5. We know that the slope is 7, and if we utilize our point slope formula, which was y minus y1 equals m times x minus x1, we can now substitute the x1 and y1 coordinates along with our slope into this equation and simplify, and then we've got our linear equation for the tangent line. So there's our substitution, distribution, and isolation of the y variable. And now, instead of point slope formula, we have our slope intercept formula, which is much more common when graphing linear equations. Now, if you didn't already look ahead, I would ask you to do so now. I do have the graph of our original function, f of x equals x cubed plus 4x, and I have the graph of the tangent line function that we just calculated. And as we look at the coordinate 1, comma 5, we have ourselves the point of tangency and a line that is perfectly tangent to this curve at that point. So I'm going to ask you to try the same process with this problem up here. Now, looking ahead, you can see that there's a solution down here, and this is the result that we're going after. This linear equation appears to be tangent to the blue curve, which was this function at this point. So we've got a tangent line to the curve at a particular point. These are the results that we're going after. Let's see if you can support those solutions with your own work. I'm going to ask that you pause the video now and complete this example on your own. Resume playback in a moment to check your work. And this is the work that I would expect to see while simplifying the difference quotient. I didn't bother to do the f of x plus h computation off to the side this time. I just completed all of that within the fraction. And here again we ended up with the derivative function. Now this function, 6x minus 4, is the first derivative of this original function. And again, I want you to be thinking about a pattern that might connect these two. If you're starting to form one, that's great. If not, we've got one more example in this video to give you a chance to practice and predict that. Well, since we have the equation to compute the slope at any point, let's go ahead and do that now. If we were to find the slope of a tangent line when x is equal to 1, as specified by this point over here. By the way, we were pretty lucky that they gave us the y value this time too. So the slope at x equals 1, we're going to use this formula that we just established. 6 times 1 minus 4. Well, that's 6 minus 4. Our slope is 2. And we have the point and the slope now given to us. So using our point slope formula, we can say that y minus y1 equals m times x minus x1. The m value is 2 that we just calculated. The x value was 1, and the y value was -1 according to the coordinate. So we now have y plus 1 equals 2x minus 2 after distributing. And now subtracting the 1 from both sides, we've got y equals 2x minus 3. And there's the equation of our tangent line. Same equation that was produced down here in the preview result. compared to our original function. We now have our tangent line tangent to this curve at this point, which was the objective of this particular question. Before we get on to the last example for this video, I do want to point out our new notation. Now, I've mentioned this first derivative, and the way we're going to notate that is with this f prime notation. We've used prime notation in geometry classes before when we were talking about translations of objects or images. You might say that, say, triangle ABC is translated to a new position, A prime, B prime, C prime. And so this doesn't necessarily mean the same thing, but I just want to point out that you have heard this phrase prime before, and this little apostrophe is what's used to indicate the word prime. And it's also worth noting that this prime notation for the derivative is not the only notation that we'll see. F prime of x is one way to identify the first derivative. Another way to identify the first derivative is with this dx, dy, or actually in this case it should be dy dx notation. These two essentially mean the same thing. There's a third. I believe Isaac Newton used dots over top of his function names to indicate derivative. But again, all of these are indicating some change in y divided by some change in x, or slope at a particular point. This first notation, the one that I'm personally most comfortable with, was credited or created by a mathematician named Lagrange. And this is a pretty popular notation. I believe he took his clues from Isaac Newton himself, because this apostrophe or dash is real similar. I believe it was dot notation that Newton used. And Newton is often the one credited with discovering or creating calculus. Another mathematician from Germany created calculus at virtually the same time as Newton, and his notation was dy dx. If I'm not mistaken, the d for dy and dx stands for difference, or a word related to the word difference. And if we look at our symbols here, which are deltas, you can see the connection between the two. But it's these two that we're going to see in this class, and we use both of them pretty frequently, so it is important to be comfortable with both. So to round out this video, we're going to talk about one more example, and this particular function is a pretty common one that we've seen, or we will see in physics class. You may have seen this in a science or physics class before, and it indicates the position of an object that's being thrown upward in the air. It's thrown from ground zero, from the ground level, but it's increasing initially at 96 feet per second, or 96 units per unit of time. The gravitational constant, 32 feet per second squared, you'll see in just a moment, but it's closely related to this notion of negative 16. So the instructions this time say to find this function's first derivative, or find its derivative. So now we've got some function notation to work with. We're not just going to say m of tangent anymore. We're actually going to say f prime of x, or the derivative of f, is equal to the limit as h approaches 0 of our difference quotient. And we'll go ahead and take some time to simplify the difference quotient for this equation. Now here again, think about the patterns that you started to develop a few moments ago, and see if your expectation for this derivative matches reality. Pause the video now and resume playback in a moment to check your work. And here again we have it, our derivative function down here, and I want to make that real clear. I'm going to move my direct substitution note. I'm going to be real clear about this. F prime of x, the derivative of f, is equal to negative 32x plus 96, and the original function f of x was negative 16x squared plus 96x. And here again, why that's so important is that this particular function allows us to find the slope of the original equation at any point. And if we jump over to this sketch over here, this downward facing parabola is essentially the trajectory of that object that was thrown in the air. Not that it was thrown forward at all, but this graph represents the object's height with respect to time. And so in time, let's just go ahead and agree to call this seconds. And we'll call this unit feet. So I don't know horizontally where this object is, but I do know that at time 0, the height of the object is 0 feet above the ground. At time 1, time 2, 3, and so on, we could calculate the height. It looks like it's somewhere between 50 and 100 feet here. Right here at time 2 seconds after it was launched, somewhere between 100 and 150, and so on. So we can establish the height using the original function, but now, and I know it may not be real clear on your handout, but now with our derivative notation, this prime notation, we're able to calculate the steepness of slope. So here this object had a slope of 96. Here the object had a slope of 64, 32, 0, negative 32, negative 64, and negative 96. Now the units of measure that go with each of these points happens to be a combination of our vertical and horizontal units. Our change in y coordinates and change in x coordinates creates the unit of measure here. So remember what I said at the beginning of this problem. This was an example of an object being thrown upward at 96 feet per second. Well, there's that calculation. F prime at time 0, the speed, or velocity in this case, is 96 feet per second. The speed at time 1, after gravity's had a chance to slow this thing down a little bit, is 64 feet per second. At time 2, we're slowing down still. The object is only moving upward at 32 feet per second. It reaches its peak, and at that instant, the object is moving upward at 0 feet per second. Downward at 32, downward at 64, and downward at 96 feet per second as the object continues to rise and fall. So the derivative is super powerful, super important. Quite a helpful tool in movement, as you can see here, but it also has its applications elsewhere. This video is getting quite lengthy, so I'll go ahead and stop it here. If you'd like to extend and challenge yourself with this particular example, I would ask that you do so, and I'll post a solution to parts A and B online with a PDF copy. Thanks for watching.